Check it out now, y'all.
NanoHub U, online instruction.
Hi again. This lecture is intended to mirror the discussion in the previous lecture, which really focused on the radial distribution of the radial probability distribution for finding an electron at a particular value of R for the hydrogen atom. In this particular lecture, we're going to focus more on the angular coordinates. And in the process, we're going to define some new operators, which are referred to as the angular momentum operators. And these angular momentum operators are going to allow us to put some real physical meaning to these separation constants, script L and M, that sort of magically appeared in the discussion of the solution of the Schrödinger's equation in the previous week's lectures. So first, just a quick summary of what we've already discussed. We've discussed the probability of finding an electron at a particular point in space, and that's given by taking the wave function squared times the volume element dV in spherical polar coordinates. We then simplified that discussion to a radial probability density, right? So now we're focused just on the radial position of the electron. We're throwing out the angular coordinates theta and phi. We integrate over them. And lastly, that allows us to define expectation values for some function of R. So if you have a physical theory that says some quantity of interest is a function of the radial position of the electron, you can find out what the expectation value for that function is by just integrating that function times the probability, the radial probability density, capital P of R. So if you perform this integral, you'll find out what the expectation value for that particular function might be. So this is the ultimate justification, right? This ability to go from this integral to an expectation value for some arbitrary function, that's the ultimate justification in my mind for this radial probability density that we've discussed. Now what we like to do is we like to do the same thing for the angular solutions, and in particular, we'd like to ask questions like, what's the probability that you find the electron at some angular coordinate theta naught or phi naught, irrespective of R, right? So forget about the distance the electron is from the center of the hydrogen atom, but just tell me what the probability density is that the electron is at some angle theta, some angle phi. So you can come up with problems that you can solve, right? You can say, give me a hydrogen atom and give it a certain quantum state. In this particular case, I picked the quantum state n equals 2, script L equals 2, m is equal to 1. And then I just asked this question, what's the relative probability that the electron will be found at some position theta 1 equals pi by 8, phi equals pi by 4, compared to the probability that the electron is at some angle theta 2 equals pi by 4, phi is equal to pi by 4. So in this case, I just keep the azimuthal angle phi the same, pi by 4. I just change the angle theta from the z-axis, right? And I'm just trying to find out where the electron is most likely to be found in a particular plane specified by phi equals pi by 4 at two particular values for the angle theta. So, once you know the quantum states, the quantum indexes, right, you can look up the wave function. In this case, we're focused on the angular wave function, so I write down what the angular wave function is for this particular problem. And in the next slide, I just go about evaluating the relative probability, right, using that wave function. And it's a straightforward calculation, right? The angle phi is fixed, that's pi by 4, so this is a plane that's located at an angle pi by 4 from the x-axis. And I've got two coordinates, two theta coordinates. One is pi by 8, the other is pi by 4. And I just want to know what the probability is that the electron is along this line or along this line, irrespective of r, right? And so I have to just basically evaluate the wave function times its complex conjugate. I have to multiply by the appropriate volume element in this plane of specified by phi, and you can just run through the arithmetic. You can double check it on your own. It's not too terribly complicated. It's pretty straightforward. But at the end of the day, what you find is that the probability that the electron is along this line specified by pi by 8, that probability is about 1/4, 27% of the probability that you find the electron along this line in the hydrogen atom. That's a nice calculation. It's interesting. It demonstrates that you understand how to use these wave functions to answer a problem like this. But if that was all there is to the angular wave functions, it wouldn't be terribly interesting. And it turns out there's a much deeper significance to these wave functions, to these angular wave functions. And I'd like to try to explain that to you in the remaining part of this lecture. So the discussion revolves around defining angular momentum operators. And what I have to first remind you of is that in XYZ coordinates, the linear momentum operators are specified in a very straightforward way, right? They involve just partials with respect to x, y, or z. And so if you operate on a wave function with this operator and you get an eigenvalue problem, the eigenvalue is then going to be the momentum along the x, the y, or the z direction. The question is, what would the angular momentum operators be in spherical polar coordinates, right? So we want to take these linear momentum operators and we want to transform them into angular momentum operators to properly describe the circular motion of the electron in 3 dimensions. So you have to know what the definition of the angular momentum in the x, the y, and the z direction is. That's a classic calculation, and I refer you to the appendix for that derivation. But what you find from this discussion in the appendix is you find that the angular momentum operator, or the angular momentum in the x, the y, or the z direction is just the product of coordinates and linear momentums, right, that are all mixed up. So for instance, the angular momentum in the x direction is the y coordinate times the momentum in the z direction minus the z coordinate times the momentum in the y direction. And using these definitions of quantum operators that we give at the top of the slide, we can then say that the angular momentum in the x direction is this funny combination y times the partial with respect to z minus z times the partial with respect to y. And you can do that for the y component of angular momentum and the z component of the angular momentum. I just list the results here, right? And it all comes from classical definition of angular momentum, considering a particle moving in a circular motion. If you just take a minute to look at the appendix, I think you'll be able to convince yourself that you understand where these quantities come from. The next step is considerably more complicated, right? Because what we like to do is we like to find out what the net angular momentum is, and that requires us to evaluate the square of the angular momentum in the x direction plus the square of the angular momentum in the y direction plus the square of the angular momentum in the z direction. And in particular, we want to create an operator called L², which gives us the square of these angular momentums. So again, we use the notation that an operator is going to have this little funny caret above each term. That tells you that it's an operator and not some classical expression for angular momentum. And so what we need to do is we need to evaluate, to carry out this plan, we need to evaluate Lx squared, Ly squared, and Lz squared. And that's simple to write because we've got on the previous slide expressions for Lx, Ly, and Lz. Now we just have to square these quantities and add them together to get the angular momentum L squared. The difficulty, of course, is this problem, the hydrogen atom problem, is not discussed in x, y, z coordinates. It's discussed in r, theta, phi coordinates. So you've got to do a transformation of variables of x, y, and z into r, theta, and phi. Well, that transformation is formidable, right? It takes about 10 pages of algebra, which is brutal. And if you're really interested, I found a nice website that actually goes through all the steps. It requires about 10 pages to work through. But at the end of the day, what you find is that the square of the angular momentum operator is given by this quantity here, right? So this quantity here is what you get when you transform these equations from x, y, and z coordinates into r, theta, phi coordinates, right? You get this partial second derivative with respect to theta. You pick up a cotangent of theta plus the linear derivative, and then you get the 1 over sine squared theta partial, or the second derivative with respect to phi. Now, also in the appendix, I show how you can go from this form to this form. This is a pretty straightforward mathematical derivation. If you're curious how that's done, just check the appendix. So this gives us a form for the angular momentum squared. This operator, L squared, is now a differential equation. And hopefully this differential equation looks familiar to you if you remember last week's lectures when we derived Schrödinger's equation in 3 dimensions, right? This is the theta and phi terms that happen to show up when that derivation was done. In addition, the other interesting operator is the angular momentum in the z direction. And again, you can refer back to this website. The angular momentum in the z direction turns out to be simpler than the angular momentum in the x and the y. It just depends on the derivative with respect to the coordinate phi. And it follows that Lz squared is just minus h bar squared second derivative with respect to phi. So these are angular momentum operators that we're going to use and discuss the solutions to Schrödinger's equation. So what I have to do is I have to remind you what Schrödinger's equation looked like for the theta and phi coordinates. And I write that down here, right? This is an equation directly from last week's lectures. And using the definition for the square of the angular momentum operator that we worked out on the previous slide, we can rewrite this equation to make it look slightly more tractable. And this rewrite basically tells you that this operator L squared times the theta and phi components of the wave functions, that's just equal to script L times L plus 1 times the wave functions back again. So this is the standard eigenvalue formula, standard eigenvalue problem, right? Notice that there's minus signs on both sides of the equation, so we can cancel that out. We can distribute at h bar through the equations. And what we find at the end of the day is we find that the square of the angular momentum operator operating on the angular wave functions is just equal to h bar squared times L plus 1 times the wave function back again. And this allows us to conclude, right, that this quantity, script L times L plus 1 times h bar squared, is an eigenvalue of the square of the angular momentum operator. So this finally gives us some physical significance that's mathematically well established, gives us some physical significance for this parameter script L that was introduced last week. You can do the same thing for the phi component of the Schrödinger's equation. what you find is that the second derivative with respect to phi that appears can be represented as the square of the z component of the angular momentum. You can use this definition to transform this equation into an eigenvalue problem, right? And the eigenvalue is now h bar squared times m squared, which basically means that this quantity m plus or minus m times h bar is an eigenvalue of the angular momentum operator in the z direction, right? So you get the plus and the minus because this is a squared quantity, right? And so when you take the square root of this, you have to basically have either a plus or a minus sign associated with it. So the really interesting thing about this discussion is that if you go through all this mathematics, you do all this transformation, you can take the standard values for angular momentum operators in x, y, z coordinates, and you can get expressions that exactly match terms in Schrödinger's differential equation that can be directly interpreted in terms of momentum, the square of the angular momentum, and the projection of the angular momentum along the z direction. So to try to make that connection more obvious, you'll find pictures like this in almost every textbook that you look at. What we're attempting to do here is we're attempting to represent the eigenvalues for the angular momentum and the eigenvalue for the angular momentum in the z direction in terms of a diagram that's somewhat easier to comprehend than all the arithmetic that we've gone through in the previous few slides. So what I've got here is I've got a sphere. The radius of the sphere is going to be given by the size of the angular momentum of the electron in a particular quantum state. The quantum state of interest is specified by the value of script L, right? So if you tell me the value of script L, then I can calculate the square of the angular momentum. I can take the square root of that, and that will then give me the size of the angular momentum vector, which is indicated by the black line in this diagram. Now that angular momentum vector is oriented in an angular momentum space that's comprised of components of the angular momentum in the x, the y, and the z direction. Schrödinger's equation gives us no information about x and y, right? We only get information about the z component of the angular momentum, and the z component of the angular momentum is this quantum number m times h bar. And remember, m is a signed quantity, so it's an integer that can be either positive or negative. So what's interesting is that because m is quantized, right, because m has specific values, that means that the orientation of the vector L in space is also quantized. And this gives rise to the notion of space quantization. In other words, the angular momentum of the electron in the hydrogen atom cannot have any possible orientation, angle theta. In fact, the angles theta that are allowed are specified by the simple geometry that the cosine of the angle is equal to the LZ component divided by the magnitude of the angular momentum operator L. And that's just given by a straightforward application of the eigenvalues that we got from the previous slide. So because m is quantized, theta is quantized, and because theta is quantized, right, we refer to this as space quantization, right? Space is not, all values of angle theta are not possible, only certain values are. The other consequence of this is that this discussion that has far-reaching implications is that we have no knowledge of Lx and Ly, right? Schrödinger's equation doesn't give us any information about those two quantities. So it's kind of useful to try to understand that puzzle, and the way to do that is to I think go back, take a step back and compare it to a classical orbit and remind yourself what a classical orbit tells you about the motion of the object. So here I have a well-defined orbit. It's positioned in an XY coordinate system. The orbit is tilted with respect to the XY coordinate system. There's an angular momentum, L, that's associated with that orbit. And that angular momentum, L, can have components in the X, the Y, and the Z direction. Classically, the tilt of this orbit can take on any value that you care to specify. There's continuous range of values of theta as this orbit is tilted back and forth with respect to the X, Y, Z coordinate systems. I focus on the Z component of the angular momentum in this diagram, so I project L back along the Z axis, right? That gives me the Z component of the angular momentum. And likewise, I can do the similar projection to get the X and the Y components. I just don't do it. The diagrams get complicated, but in principle, you know all three components of the angular momentum for a classical particle moving in a well-defined orbit. What happens in quantum mechanics? Why is it so different? Why can we only know the Z component of the angular momentum? Well, in quantum mechanics, the particle is now represented not by a particle, but by a wave. So there's some wave that I've schematically indicated in this diagram, right? And that wave is delocalized in space. Because that wave is delocalized in space, the plane of the orbit is not well defined. It's not as clear as it was when the particle was a classical particle, okay? And the consequence of that is that only one component of the angular momentum can be known, and that component is the Z component of the angular momentum. The magnitude of the angular momentum is also known, but its orientation, right, its position along the orbit is not well defined simply because the electron is represented as a wave. So this is an attempt to try to explain in a hand-waving way why this funny space quantization results in quantum mechanics, and it ultimately comes back to your inability to precisely define the orientation of this orbit simply because the electron is represented as a wave and not a particle. So you have to think about that a little bit. What we're going to do in the next lecture is we're going to develop this model for angular momentum. It's quantum mechanical, it's strictly quantum mechanical, right? There's no analogy to classical physics, but we're going to develop that into what is known as the vector model for angular momentum, and we're going to discuss the results in a little bit more detail, try to make it a little bit more transparent what those results mean. So come back to the next lecture and we'll do a little bit more on angular momentum before we move on to other topics.